Hello, everyone. Welcome to Socorro's webinar series, Coastal Observing in Your Community. My name is Abby Wakely, Socorro's Director of Communications, and I will be facilitating and moderating the webinar today. Socorro is hosting this webinar series to discuss, highlight, and raise awareness about coastal ocean observing activities in the Southeast U.S. and beyond. Socorro is the regional coastal ocean observing system for North Carolina, South Carolina, Georgia, and Florida. We are one of 11 that make up the NOAA-led U.S. Integrated Ocean Observing System, also known as USIUS. Our mission is to sustain and promote observations that help keep you safe. This is a quick snapshot of the technology we support to accomplish our mission. All right, let's get to the reason you are all here, the webinar. During the webinar, we highly encourage you to ask questions for the presenters or technical questions for me by clicking the tablet-looking icon and typing in your question. I will pose them to the presenters after their presentation. And as a reminder, this webinar will be recorded and a posting of the recording will be on the Socorro website. We are very excited to welcome Drs. Stephen Meyers and Dr. Mark Luther from the University of South Florida College of Marine Science. They will be presenting initial results predicting high cross currents near South Florida ports using machine learning. Dr. Stephen Meyers is the Chief Scientist at the Center for Maritime and Port Studies at the University of South Florida College of Marine Science. He has over 20 years experience working with estuarine circulation models, climate variability, advanced data sets, and more recently, artificial intelligence and machine learning. His work focuses on solving problems related to maritime operations, coastal infrastructure, and estuarine management. Dr. Mark Luther is an associate professor and director of the Center for Maritime and Port Studies at the University of South Florida College of Marine Science. He has worked in real-time ocean observing systems since 1993 and was involved in planning and implementation of the U.S. Integrated Ocean Observing System from its inception. He works closely with the Tampa Port Authority, the Tampa Bay Pilots, U.S. Coast Guard, and other maritime interests on environmental issues affecting and affected by maritime transportation operations and infrastructure. Thank you guys so much for joining us. Steve, I am going to promote you to presenter so you can share your screen. So you should be getting a prompt right now.
Yeah, there it is.
Perfect. And I am seeing your screen and the presentation. All right, Mark, you can go ahead and kick us off.
Great. Well, thank you folks for joining us today. Again, Abby did a great job with the introduction, so I won't say much more about that. But again, I've been the local operator of the NOAA Physical Oceanographic Real-Time System for Tampa Bay since the early 90s. And so we've been looking for ways to make real-time ocean observations and short-term forecasts more useful to the maritime community, which sort of led to this project. Next slide, Steve. So again, Tampa Bay Ports was the first of its kind, but now there are 38 NOAA port systems around the U.S. at critical port locations. Miami is one of the more recent ones. It went online with its ports system in 2017, and just before it became online, I visited the Miami pilots. They're actually called the Biscayne Bay pilots. They had implemented what they call the IATON. It's a Nortec ADCP. I think it's about 1200 kilohertz. Clamped onto a standard Coast Guard channel marker buoy, as seen in the image here. You can see the mounting system for the IATON at the lower portion of the buoy, just under the letter M. There's a composite fiber tube that gets the ADCP head below the ballast weight on the bottom of the buoy, and then there are boxes for the telemetry electronics and battery packs. The whole thing clamps onto a lifting eye on the buoy. You can see the Miami Ports data at the link there. They have 3 of these IATONs on the sea buoy, which is pictured here. buoy 1, which is the entrance to the dredged part of the channel, and buoy 3, which is close to a little dog leg in the channel that goes into the main port facility. The reason for putting these things in is that they frequently encounter strong currents across the ship channel entrance that are associated with the Gulf Stream or Florida current as it meanders toward and away from the channel entrance, that causes problems for bringing big ships like the container ship in the background of the image there frequently encounter. Next. So here's a nautical chart, and you can see the sea buoy is the RWM at the entrance to the channel, and the depths here are in feet. So out at the sea buoy, it's about 200 to 300 feet deep, but it very quickly shoals up to about 25 to 30 feet deep as you move towards shore. You can see the ship channel indicated by the dashed lines there. And it's dredged to 52 feet, and it's fairly narrow. It's only about 600-700 feet long. The big container ships and cruise ships that come in and out of the Port of Miami, those are the only two things that come in and out of the Port of Miami, are 12 to 1,300 feet long and are drafted to 48, almost 50 feet in some cases. So if there's a strong current across the entrance to the channel, the vessel is in danger of being swept off to the side of the channel, where it goes from 52 feet to 20-some feet very quickly. And it's a box. The channel is a box cut through lime rock, and so if they stray out of the channel, it could cause serious damage to the ship. It's not soft sand like we have down here in Tampa. So they really need to know what the cross currents are to make that approach. Right now, they get the real-time data from the ADCPs on these navigational channels, but in visiting with them, I did my dissertation back in the late 70s, early 80s, I'm an old dude, on meanders of the Gulf Stream. And so I thought, well, these meanders propagate along shore, along the inshore edge of the Gulf Stream. So if we know something about what the Gulf Stream is doing upstream of here, perhaps we can predict when they might expect these adverse cross currents to impact their operations. Next, please. So just for those of you who might not know about harbor pilots are men and women. Every major port in the world has a group of harbor pilots or bay pilots or river pilots that are seasoned mariners, typically with decades of experience on ocean-going vessels, that specialize in guiding vessels in and out of a particular harbor, because every harbor is unique in many ways, and people, the masters of large ocean-going vessels can't be expert in every port that they call on. So when a vessel enters a port, a harbor pilot, the guy to the left of this screen, Pilot Jeff, is taken out to the vessel on a small pilot boat, typically about 50 to 60 feet long. And the pilot boatman is on the right there. He's driving the vessel, and the pilot is talking with the master of the vessel. And they'll pull up alongside the ship. Next, please. And the boatman will match his speed, or the pilot boat speed, to the speed of the vessel. In this case, we're going about 11 or 12 knots alongside this 1,300 foot long container ship. And the pilot will then climb a Jacob's ladder up to entryway to the ship, sometimes all the way up to the main deck of the vessel. In this case, there's a stairway about 15 feet above where we are. Jeff invited me to ride along with him, but I only have one arm that works. I didn't think I could climb that rope ladder very well, especially if I fell off, I'd quickly get sucked into the props of the vessel. So I thought I would politely decline. So anyway, and once the pilot gets to the bridge of the ship, they basically take control of the vessel. The master of the ship, the captain of the ship, is still ultimately in command, but the pilot is issuing steerage commands to the helms person on the vessel. If they do have strong cross currents, they have to increase their speed to maintain their steerage so that they don't get swept off to the side. But the more they increase their speed, the more the vessel squats down in the water, and so that decreases their under keel clearance. So knowing what these cross currents are ahead of time is very important. And if they know, say, 24 to 48 hours ahead of time, then they can schedule the arrival of the vessel to avoid the instances of these strong cross currents. That's what motivated this study. And talking to the pilots down there, we decided that we would seek some funding to play with the data both from the ADCPs and the Miami port system, but also take advantage of whatever other data on Gulf Stream frontal positions we could garner from upstream, either from Nick Shea's HF radar network or models or the Navy's frontal analyses of the Gulf Stream. So Steve and I have been playing with that for some time. We got a little bit of funding through the Socorro Gap mechanism to do this pilot study. So Steve's going to talk about the nitty-gritty details of what we've been doing since. Take it away, Steve.
Oh, thanks, Mark. Everybody can hear me? I hope. Okay.
We can hear you, yep.
Good. Hi, everyone. I'm Steve Meyers. I understand that we have something of a mixed crowd today, so I'll probably gloss over some of the deeper mathematical details here, but I'm happy to discuss those separately or after the presentation. So on the right here, this map shows the location of the three major ports in South Florida: Port Palm Beach, Port Everglades, and Port Miami. And I'm going to talk a little bit about the vessel activity in and out of these ports and the hazardous currents that they encounter. So our objective here was to create a machine learning tool that can predict the occurrence of these hazardous cross currents. Right? And I'm going to talk a little bit how we developed that, the methods that we used, and then how we evaluated that model, because that's very important. Once you take a model, you have to test it. And then we'll talk a little bit about future directions. So in the middle here is a plot of all the medium and large vessels, that is vessels greater than 50 meters in length, that visit the ports indicated on the left each month from 2015 through the end of 2020. So that's not the number of transits, it's the number of unique vessels. And the black is the total number of vessels detected. This is based on records of vessel traffic that that's collected by the government. And then we looked at what kind of vessels are moving in and out. Well, the four most common types are cargo vessels, tanker vessels, passenger or cruise liners, and recreational. So at the size we're talking about here, when I say recreational, I'm talking about yachts. And you can see certain things, different characteristics for the different ports. One thing they have in common is strong seasonality. That's because, for example, in Port Palm Beach, the yachts are not very active in the summertime. There's a lot more of them in the wintertime. All right. And the same is true for Everglades and Miami, but they also have experienced the seasonality of their passenger vessels. The cargo and tanker vessels, not so much, they're relatively steady. Another thing you might notice is that in 2020, things look a little bit different than they do in previous years, and that's because of the pandemic. That's something else we're looking at separately. So on the left are the navigation charts for these three ports, and you can see their access channels, and they're oriented roughly east-west. So that means that the vessel traffic in and out, and these are the vessel tracks, vessel traffic in and out is also oriented east-west, which is a problem when you have these strong Gulf Stream currents, which are flowing to the north. So as Mark mentioned, NOAA installed 3 ADCPs, which are current sensors, in the outer portion of the Miami Channel. And we're going to be focusing on the outermost sensor. This is data from the sensor. The uppermost plot is the current speed. This is over about 3 years. And we see that the speeds range from 0 to almost 200 centimeters per second. But the majority are less than 50. You can see there's a big swings in current direction. If you look at the third plot though, which is a scatter plot of speed versus the direction, you'll see that the highest speeds are almost exclusively oriented to the north. There's also a secondary speed maximum where the flow is actually to the south. The lower figure is a technical distribution plot I won't go into right now. But these large currents, particularly the northward currents, are dangerous for ships that are very large and very deep. So I say it's deeply drafted, right? It's a lot extends deep below the waterline. So because that large area acts as a sail, so it picks up the momentum of the current when it's coming in perpendicular, it picks up the momentum of the current and then can sweep it into the limestone channel, which cause damages to the ship, potential loss of cargo, and dangerous personnel. So it'd be good to have a prediction of that. All right. Oh, a point here is that the current speed is greater than 100 centimeters per second 3% of the time. So that's a piece of trivia I'll come back to in a moment. So I mentioned the larger ships are in more danger of this. So this on the left here is a scatter plot of the ship draft, its depth below the waterline versus its length. And we see that the larger ships are generally more deeply drafted. But if you partition that up by vessel class, the passenger ships, the cruise liners, are much more shallow than the cargo ships and the tankers. On the right is a plot of the current speed versus the speed of the ship actually coming in. There's a couple of things you can see here, that the ships have an operational speed limit around 15 knots. And they seem to be coming in more frequently at the lower current speeds, but 3% of the time, right, it's 100, they're coming in when the currents are 100 centimeters per second. So this data is from 2018. So this indicates that the passage of the ships in and out of the port were being done irrespective of the currents. So remember the ADCPs were installed at the very end of 2017. Now I looked at the 2020 data. I don't have that to show, but this 3% dropped to 1%. So it seems like the pilots are using information from the ADCPs to better time their vessel transits, but we're talking to them now and trying to verify that. So this is a zoom in of about 2 months of the outermost ADCP. This is the current speed. And this is the problem here, right? So you can see that the currents will jump from 15 centimeters per second to 120 or higher in a matter of a few hours or a day. And that the occurrence of these high speed events is irregular, and the duration is also irregular. That makes it difficult to predict. So as Mark said, we're basing this on a hypothesis that these events are caused by the propagating meanders of the Gulf Stream, shifting its position east-west, right? Westward would be onto the access channel, and back to the east would be off the access channel. So in order to verify that hypothesis, we need a lot of data. We need to be able to examine the meanders, the Gulf Stream position at reasonable spatial resolution and a pretty good time resolution as well. There's not a lot of observational data that provides that. So instead, we started our study looking, using output from a global ocean model, which in this was the hybrid coordinate ocean model, also known as HICOM. And we took about 2 years of data, sampled from South Florida, and this is about time steps of every 3 hours. I'm going to skip, the point here was that the outermost ADCP is right next to a model grid cell, so we can measure, get the estimate, the model velocity right at the ADCP, right? So we also have the velocity field of the model from that extracted region, and then we can compute the mean current speed, right, over those 2 years. And this is the plot of the HICOM mean current surface speed. And you see that as with a general flow direction indicated, you can see that the current narrows and intensifies as it bends around the southern tip of Florida. Right? And then the meanders shift this back and forth over time. So we need a way to quantify that meandering. And that actually turns out to be a little bit tricky. There's a few ways to do it. It's easy to do it for 1 or 2 time steps. Right? You can just look at, say temperature isolines, or you can look at current speeds. But we also need a way, but as you go through time and the topography of the Gulf Stream changes, you can't necessarily look at differences in sequence, right? Because it's like you have a different, the framework changes. So we need something that's a way of measuring this that's consistent with the physics, and that is stable over time. So what we are using here is a series of this polar sampling that's in a fixed frame, right? And this is useful because the sampling is roughly perpendicular to the flow, and the meanders are roughly perpendicular to the flow. The curve, it follows the curve of the current as it turns around South Florida, and this is also a fixed framework. So what we do then is we can we define the position of the Gulf Stream along each of these lines, defined as the position of the maximum current speed. So we do that for all of the time outputs that we have, and we find the mean. That's the red dots here. And then we can look at the deviations from that mean position along each of these sample lines. Right. So again, we're using the maximum current speed as the definition of the Gulf Stream position. All right, so now we want to test whether the meanders are, first of all, are they significant? Are they even detectable? Well, we're looking at the lag correlation of these deviations, this is the lag correlation. The vertical coordinate is the axis or the arc index. So the first one is the one to the south, and the last one is the northernmost arc line. And that one, by the way, that one is co-located along the latitude of Port Miami. And you can see the propagation structure here. For the non-technical audience, lag correlation is a way of looking at quantifying time delays in a signal. And it goes from 0 to 1, or actually -1 to 1. And so we're here, this is lags of 1 day, 2 days, 3 days, and we have the progression along the arc samples in the vertical axis. So at a day lag, right? We're getting correlations around 0.8, which is pretty good. And even at 2 days, we're getting something over 0.6. Right, so that is encouraging. That's kind of what we expected to see. Right, so this kind of these sloping lines are indicative of a propagating structure, which are the meanders. So that makes us think, well, maybe we could use that to predict the current speeds at the port. Well, we tried that, and that's these desert colors. It's the same kind of lag correlation here, but you'll see that the numbers are much lower. They're like 0.15 or so, which is really not, means that they're really not correlated. There's no strong correlation there. So we can't really use the meanders by themselves to create a quantitative prediction of the current speeds near the port. But if we look at, okay, this figure is a little bit complicated, so bear with me. All right, so this is our distribution plots of the current speed in the model, right, at the grid cell that corresponds to that outermost ADCP. And the horizontal positions are the location of the maximum current speed to the east of that one grid cell. So the ADCP grid cell is just to the left of this line. Then we have one grid cell over, two grid cells over, three, right? And this is the distribution of the velocities at the ADCP corresponding grid cell, right? So when the maximum speed is at, say, the second grid cell away to the east, that happens 7.9% of the time, and you get the maximum correlation, maximum current speed, mean current speeds, which are indicated by the circles, plus or minus the standard deviation is indicated. So you can see here that as the current position gets closer, moves further to the west, the current speeds increase on average. And you can also see that the very highest current speeds only occur when the Gulf Stream is shifted furthest to the west. All right, so this suggests that instead of doing a quantitative prediction, we could do something categorical. Right? Just, is it extreme? Are the current speeds extreme or not? Safe or unsafe? So to do this, we use something known as logistic regression, which is a binary classifier. It basically provides the probability of some variable being in one of two states, where there's a single transition between the two. So it could be, it's 0 or 1, yes or no, up or down, safe or hazardous. And the structure of this binary model, this logistic model, is based on the log of the odds ratio, and it's equal to the summation here, which is a sum of the independent predictor variables, which are something that we're going to have to choose. In our case, it's going to be the deviations of the Gulf Stream position along each of those arc rays, right, times some fitting coefficients, which are determined through some mathematical techniques I won't go into right now. So what do we want to do? We want to predict the probability of, we want to use this to predict the probability of the currents being above or below some threshold. Right? The thresholds we're using, this is done in 4 steps. Sorry, the first one is the choice of the predictor variables. So as I said, these are going to be the displacements along the arc lines. And we're going to, because we have the lag correlation, we can use that to determine which one are most highly correlated at 12-hour delays, 24-hour delays, and 48-hour delays. So I'm not going to talk about the 48-hour because it's adds more complication, and our initial talk with some of the people, some of the pilots, suggest that 48 hours is not really useful, since they don't necessarily know if a ship's even coming in until about a day before, So 24 hours is most useful. So the prediction thresholds, right? We have to choose, well, we don't know which is the best velocity threshold. So we looked at a few of them. And we looked at certain factors of the standard deviation above the mean. That factor ranged from 0 to 2. And then we partitioned the predicted variable, which is the velocity field. Is it above or below the particular threshold? Then we determined the fitting coefficients, right? And then there's some mathematical techniques in there where we have to check for overfitting and compensate for something called unbalanced data. I'll get into that in just a second. And then we have to evaluate the accuracy of the model. We do that in a couple different ways. So I won't run through all the details here. To check the sensitivity of the model, whether there's always a concern when dealing with AI or any kind of machine learning algorithm that somehow the data, your model won't work beyond the data that you're giving it. Right? So the way you do is you throw out parts of your data set and then you rerun the model and then you see if the model changes. So we do that, we throw out sections, 20% of the data in separate sections, and then we refit the model and we look at the mean of those coefficients compared to the coefficients generated when we fit the model to all of the data. And those coefficients varied, they all varied less than 10%, and almost all of them varied less than 2%. So that means that the model that we're creating is not overly sensitive to the data that we're giving it. So the second trickier issue is class imbalance. So this occurs even in linear regression. So you can look at this example, this schematic here, where we have the blue data and the orange. So the blue data is the more popular one, or the larger subset. And this is, in our case, this would be values below, occurrences below our threshold. Remember, we're looking at very high extremes, so they're relatively rare events. So if you were to collectively fit the blue and the orange data, you might get a line like the black line, and which really doesn't characterize the aspects of the system that you're looking at. So the way to deal with that, and there's all sorts of ways, techniques here, but what you do is you reduce the number of blue data that you put into your analysis. We just kind of did this randomly. We sampled the blue data the same number of times as the orange data, so there's an equal balance there. So when you do things like that, then you get something more like the green line, right, which represents the aspects of the system that we're most interested in. All right. So having done all that, all right, how do we know if this model's any good, right? So like I said, that the logistic regression provides a probability of a variable being in one state or the other. So first thing we do is we can define some critical probability threshold, right, which we're going to call hazardous. And below that threshold, then it's hazardous. If it's below, then it's not. And we can look at each occurrence, whether it's a true positive, true negative, false positive, false negative. Those terms are fairly self-explanatory. I don't think I need to talk about them. But then we look at the whole collection there, right? True positive rates, true negative rates, false positive rates, false negative rates. So this is more of a collective measure across the entire model. So like the true positive rate. So that would be the number of correctly identified positive values, or hazardous values in this case, compared to the actual number of hazardous values, right? And so on for the other measures. These are commonly compared in what's called a confusion matrix, which is a 2x2 presentation. And I'm giving you 4 examples here. One for the 12-hour prediction, one for a 24-hour prediction. The columns are 1.5 standard deviations above the mean and 2 standard deviations above the mean. So you'll see that for the 2 standard deviations above the mean, the true positive rate is over 90%. That's good, right? It's even better than 1.5 standard deviations above the mean. So that makes sense. If you think about the blue and the orange plot, right? As you move further away from the blue, that model fit becomes cleaner, right? It's more pure orange, right? Whereas if you're moving more towards an overlapping region, there's a little bit more ambiguity. So that's why the more extreme values are better predicted by this model than the less extreme values. Also, the false negative rates for the 2 standard deviation study are single digits. So that's very good because false negative rate are when you falsely think that something's safe. You say, okay, it's safe to go, but in fact it's not, right? So you want that number to be very low. The other 2 numbers are moderate. We're looking at ways to improve those as well. And by the way, this is all for threshold probability of 0.5, which is the most common value chosen by most researchers. However, there's no real hard and fast rule on that. It could be any particular value. So I mean, if you have a system where the consequences of error are very high, you might want to lower that threshold. Right? Whereas if you have something that's very safe, with little consequence if there's a problem, you might raise that threshold so you can stay in operation more. So how do we look at this more broadly without having to choose a probability level? Well, we use the receiver operator curves. So this was developed in World War II for the receiver operators that for the early radar systems. Right? This is how they quantified the accuracy of whether what they were seeing on their screen actually corresponded to something out in the field. So I'm showing 4 cases here, 24 and 12-hour prediction with 2 different sets of predictor variables. One just being the deviation of the Gulf Stream along those sampling lines, and the other being that plus winds. Right? A perfect model would look like the red line in the upper left. And we see that and the diagonal line is random junk. It's a completely useless model. Right? So that's your range in there. We see that in all cases. I'm sorry, I don't know if you can, I think you can see it, that the different colors are the different thresholds. So the brown, which is closest to the upper left corner, that's the 2 standard deviation above the mean, right? And the next one, that kind of purplish one, is 1.5 standard deviations, right? And then as you move closer and closer to the diagonal, that's the lower thresholds. Right? So the addition of the wind raises those lower thresholds, improves those a lot, and also improves the higher threshold tests as well. We can measure that improvement using the area under the curve, which is basically, it's literally the area under these curves, okay? So a perfect model would have a value of 1, and the useless model would have a value of 0.5. And below that, you start getting into like anti-correlation. But none of these are below 0.5. They do range from about 0.5 to 0.8. The addition of the winds raises it, our area AUC values to 0.89, 0.88, which is pretty good. I mean, remember, this is just a very simple model that we've been using. So in conclusion, using physics to basically our understanding of the mesoscale hydrodynamics of the system was very useful to guiding our selection of variables. We're able to reduce the possible variable set to a very small number. Now, this is completely different than the way most AI and machine learning systems are going these days, where they're using hundreds, thousands, some are even using, a million different input variables. And those are very different kinds of problems, of course, but this shows that the power of understanding the system can really provide a lot of benefit in designing these kinds of models. So reducing that variable set also enables you to train your model with less data. So if you have a lot of different variables, you need a long time series to fill that parameter space. Whereas if you just have a few variables, you can fill that parameter space with a shorter time series. Also, doing the categorical approach was very useful here. And we are talking to some of the pilots really soon down in Miami to see what's kind of thresholds they find most useful. Now, remember, this was all done based on HiCom output. Right? So HiCom has limited resolution, which means it has certain limitations. So, for example, the most relevant here is that while it does get the meander propagation well, it doesn't necessarily get the timing of those meanders very well. So you really can't use the HiCom for an operational tool. And so we're looking at the HF radar that Mark mentioned at the beginning of this talk. That's a complicated data set, and it requires a lot of time. Off Miami, the HF radar system was down for quite a while. It only started operating again last year. So that's has a lot of potential for providing the kind of data we need to turn this into an operational tool. And finally, I just want to mention that this kind of algorithm can be applied to any port that's near western boundary current that has these same kind of meandering currents in its vicinity. And there's quite a few in the world. So thank you. Let me know if you have any questions.
Thanks so much, Stephen. We've had a few questions come in. Christina Forbes, if you actually want to continue sharing your screen, I think this is going to be related to like slide 4. I tried to count, but I might give off.
Can you see the PowerPoint?
Yes, I can.
Okay.
So I believe it's slide 8. She had a question on about ADCPs. So Christina Forbes, she asked, at what depth are the currents from the plot, or are they 1 meter deep from the left plot?
Okay, so these plots are from, this is the uppermost bin. And the first, let's see, the sensor depth is 2 meters down. And so we're looking at roughly 3 meters from the surface.
Perfect. And then she asked, up to what depth is the HiCom average current?
Well, the HiCom has multiple levels, all right? And it's a hybrid system, so it has fixed levels at depth and then variable levels, isopycnic levels at near the surface. So what we're doing there is we're just looking at the very surface currents on that. Was that what you? I think that's what you're asking. So yeah, so we're taking the uppermost level from the HiCom model when we're doing this project.
Perfect. Yep, that's the question that was asked. And then we had another question come in. What is the propagating meander?
What is a propagating meander? So it's a wave, right? So if you you take a string and you wiggle it, right, you get a wave and it propagates down the string. Well, something very similar happens to these very strong, narrow ocean currents, right? They have this kind of instability as they're moving over topography and the winds hit them, or they encounter other currents. They can start wiggling, and then the wiggle propagates just like it does down a string.
Yeah, the Gulf Stream basically wiggles from side to side due to these inherent instabilities. In fact, you can look at Luther and Bain, 1985, in the Journal of Physical Oceanography, page 1, and references therein. John Bain and I and other collaborators did a lot of work on these Gulf Stream meanders in the South Atlantic Bight around that time frame. So, but again, it's a wiggle from side to side of the current itself, and particularly in the inshore frontal boundary of the boundary current itself.
Thanks. And there was
go ahead.
A follow-up. Is it chaotic, highly nonlinear?
Yes and no. I mean, the dynamics of it are fairly nonlinear because it results from instability processes in both barotropic and baroclinic instability processes in the flow field itself. And so once the meander is established, though, it moves downstream along the inshore edge of for a frontal meander, it moves alongshore at a fairly predictable speed. But again, the generation of these meanders is fairly chaotic.
And you can see that propagation, that steady propagation, in those lag correlation curves that we showed, where you get those sloping lines cutting across. That's indicative of that steady propagation, or near steady.
And in this part of the Gulf Stream, known as the Florida Current, the meanders are constrained by the bathymetry because it's flowing through the Florida Straits. So the meanders are fairly small amplitude, a few kilometers, maybe up to 10 kilometers, whereas you get north of the Florida Straits, they get much larger. The Gulf Stream there can meander side to side relative to the direction of the flow field by 30 to 50 kilometers. And so that leads to all sorts of other processes, shelf edge upwelling and things like that, that turns out that fishermen in that part of the world have known about for quite a long time, but we didn't really start looking at it until the late 70s, when we started having satellite AVHRR imagery, where we could actually follow the meanders in near real time, which is what fed my dissertation.
Great, thanks, Mark and Steve. Another question came in. Can improvements be made using higher resolution models or satellite data?
I did a quick check. There's a higher resolution version of HICOM that's specific to like the Gulf of Mexico, Caribbean region, and the results were very similar to what we got with this model. So it's going to be, and the real issue then is not so much the resolution as the model ability to get the timing of those meanders right. And that I don't see that. I may be wrong, but I don't see that happening in the modeling world in the near future.
But of course, because these instability mechanisms can originate at a smaller scale, the higher the resolution, presumably the more faithfully the model might pick up those meander instigation or generation events. But that's just speculation at this point.
Right.
Thank
You'd
you
have to
both.
get a good resolution, I think.
Understood. Another question came in. Could you elaborate why wind improves the model results?
Why wind improves the model results? Well, I have two answers. One from a machine learning point of view is that it just does, right? I mean, a lot of AI machine learning is done as black box, and what they do is they'll just throw in a whole bunch of variables and do some statistical tests and shake it out, see what shakes out, and then they use those variables, right? So we did something like that here. Now, from a physical point of view, because we're actually looking at the northward component of the wind, so the wind can actually accelerate. If the wind is strong, it can actually accelerate the current a little bit. And so that's why I think that's why we're getting improvement when we add wind as a predictor.
And from a harbor pilot's perspective, these big ships have enormous sail area above the water line that can be influenced by winds on the beam, as they say, winds perpendicular to the direction of the vessel's movement. So, so from a safe versus hazardous standpoint, the wind does play a role in that determination as well.
Great, thank you both. Another question has come in. Sounds like most of this prediction is mesoscale. How much do sub-mesoscale dynamics contribute to the hazardous currents the pilots deal with?
Well, the two primary contributors to these currents in the real world are the meanders and the tides. Right, so there's a lot of the meanders will shift things around, but it also gets modulated surprisingly quite a bit by the tides. So that's that's the other main frequency that's in there in the real data, in the observational ADCP data. So we get the longer, lower time frequency signal from the meanders, and then we get a strong tidal signal as well. I have not looked at any other frequencies in detail, so I'm not sure about that.
And from a harbor pilot's perspective, that's why they have 3 of these downward-looking ADCPs, current sensors, on these nav buoys. Buoy 3, the inshore-most current sensor, is near that little dog leg, and there the currents are more dominated by tides than they are by what's happening offshore. Whereas out at the outer, the sea buoy and buoy 1, the current speed there is more dominated by the position of the Gulf Stream, but as Steve said, modulated somewhat by the tide. The deeper you go, the less the tidal influence.
Thanks, Mark. Thanks, Steve. And we had another question. Oh, this is a follow-up to that question you guys just answered. Would adding tide into the model help with timing?
Yeah, if we had well, right now we're limited to the HICOM. Once we have more in situ data, say as the HF radar data builds and there's enough of it to create a good regression model, then we can add the tides in. But right now the timing, we can't do that with the HICOM. We're just, we have to use what it outputs, and it doesn't do the tides very well.
Great, thank you guys so much. And I wanted to follow up. Christina Forbes is asking a lot of these questions because United States Coast Guard Search and Rescue, they use surface currents at 1 meter for drift modeling to generate probability maps. And it is generally difficult to find models or observations at that depth. So that's where a lot of these questions are coming from. So I'm going to connect you and Christina together so you guys can have an offline conversation. And then she had another question as we follow up. Would the different in depth of ADCP and HICOM surface currents influence the data analysis?
No. The way we are setting this up is we have, it's going to be the models based on HICOM, and then the model based on the observational data, whether it's HF radar or something else. So the principle is the same, right? We would need, if as long as the HF radar can, swings far enough south, and I think it does, and we can get the current speeds there, then we can look at the meanders as they move, as they propagate along the Gulf Stream. But the different depth, now it all depends. The ADCPs, like I said, they're, I think the first bin is about 3 meters below the surface. So that's where we would start. That's what we're limited to when we start applying this as an operational tool. So we could not do 1 meter. And also remember, this is we're just looking at a single location, right? We're not, I don't know if it would be very useful for search and rescue. This is something that's really designed specifically to help the harbor pilots with their decision to bring a ship in or out.
Great, thanks so much, Steve. We had another question come in. If you expand to other ports, what type of in situ data do you need to validate the model?
Same as here, we would, if we wanted to do in situ data, we would need some sort of extensive current velocity field, right? Current field over time, a year or two, every few hours, all right? So we can get the tidal signals as well as the any seasonal changes, all right? And it has to be quite a bit of it in order to develop these regression models. So yeah, the bare minimum would be the surface current field. If there's a nearby tide gauge, that could help as well.
And a wind sensor, perhaps, wind was a factor. So basically, a whole port system.
Another question has come in. Have you tried using satellite allometry